could be some deviations associated with that when the situation is very large. But it has to do a lot with how you filter, right? I mean, the simplest example is the following. In principle, the critical current that you're measuring doesn't disappear ever. It becomes smaller and smaller and smaller, but theoretically it's there forever. Obviously, we can't measure it beyond a certain value, so you can immediately see that what we're measuring is some kind of square multiplied by the real thing. That square leads to oscillations, and these are those.
One more question.
So in any semiconductor, you will have edge states because of just banding, some form of edge state.
Right. So
the question I have is, can you detect those using this technique?
So sure. I mean, so first of all, let me mention that some semiconductors, the edge properties are such that the Fermi energy actually wants to sit in the gap, not sit in the conduction band. Gallium arsenide, for example, it's very hard to measure, hard to make the surface of gallium arsenide conducting. There's no way you're going to do it. Indium arsenide, on the other hand, will have all its surface states sitting inside the conduction band, so there you will have a conducting state. From whatever is known today about mercury telluride doesn't seem to have these kind of surface states with this metallic density. So it's not believed that there is any pinning of Fermi energy at the surface as you have in indium arsenide or gallium arsenide. So that's the current understanding, that this system doesn't have this kind of band bending sitting at the end. But this technique is impartial to whatever is causing current flow to be at the end. I just want to point out that the 4 nanometer versus the 8 nanometer quantum well, it's just a change of 4 nanometers, and yet these edge modes are not there. So it's a very strong pointer that that's not the origin of the effect.
Okay, if there are no more questions, let's thank the